So today we're going to start looking at how we're actually going to work on counting things. Okay. So the big point of this unit is that we're going to have situations of things that are happening, and we're going to have to decide how many possible ways are there for this event to occur. Okay. So tree diagrams are a method that you can use to organize how something is happening so that you can then count them. Okay. So for example, here, flipping a coin 3 times, right? So if you could like make a list of like, okay, well, you get heads and then heads and then heads, or heads and then tails and then heads, or tails, heads, tails, or tails, tails, heads, right? So you could like make out a list, but you have to make sure if you're going to get all of them, right, you have to have some sort of an organization to it. Okay. Because if you don't have it organized, it's going to be really easy to miss things. Okay, so what a tree diagram is it's a method that you can use to help you organize so you can count all the possible ways something can happen. Okay, so flipping a coin 3 times. So flipping a coin, that would be our event that we're talking about. So our event is flipping a coin. All right, and when you do that, the possible outcomes are there's 2 of them, right? You're either going to get heads or you're going to get tails. All right, you know how coins works, right? So those are your 2 possible outcomes, heads or tails. So you can see over here, I kind of just put this tree diagram on here. So it's set up where each kind of column is one of the 3 events: the first flip, the second flip, and then the third flip. Okay. And then what we're showing is what happens then. So the first time you flip a coin, you're either going to get heads or tails. Those are the only 2 things that could happen. Okay. When you flip the coin the second time, we've got some more outcomes that could happen. Like obviously the second flip, you're either going to get heads or tails. So you could have gotten heads the first time and then get heads again the second time. Or you could have gotten heads the first time and then gotten tails the second time. Okay. Similarly, if you've gotten tails the first time, you could get heads the first time. If you've gotten tails the first time, you could get tails the second time. Okay. So looking at what we have right now, if we were just talking 2 tosses, that would be the end of our tree diagram. And there'd be a total of 4 possible outcomes, right? Heads, 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 tails, tails, heads, tails, tails. Okay. So the nice thing about tree diagrams is that when you get to these last branches, those are kind of the ends of all the paths. So if you just count up this end, 1, 2, 3, 4, it tells you that there are 4 possible ways to flip a coin twice. Okay, so now when we add in our third toss, we have even more options, right? If you got heads the first time and heads the second time, you could get heads again. Or if you got heads and then heads, you could get tails this time, right? So there's 2 outcomes. Okay, if you got heads and then tails, you could get heads. Or if you got heads and then tails, you could get tails. So there's 2 more outcomes. Right? Similarly, down here, if you got tails and then heads, there's 2 outcomes. If you got tails and then tails, there's 2 outcomes. So since we can look at this and see that there's 1, 2, 3, 4, 5, 6, 7, 8, there's 8 total end trails. There's 8 different ways to get to the end of these paths. Okay, that tells me that there's a total of 8 different ways that you could flip a coin 2 times. So 3 times. So when you flip a coin 3 times, there's a total of 8 different ways that could happen. Okay. So key difference here, right? A tree diagram is a way to illustrate what all of those options are. Okay. You can use it to then figure out that there's 8 different ways. But the point of a tree diagram is not to count the number of ways, it's to display them all. It's to make a big list of all the different ways to do it. Okay, so let's take a look at this next one. So Miss King decides to rearrange her rooms into groups of 4 people. Usually my classroom is arranged into groups of 3. Okay, so in this case, we're rearranging into 4 people. So we think about it, we got a group of 4, right? And I've got seats 1, 2, 3, and 4. Okay, and what we're doing is we're going to assign these 4 people, right? Trevor, Ray, Julie, and Vernon to each of one of these 4 seats. Okay. So how am I going to make my tree diagram? Well, I'm going to split this up based on what my choices are. The first thing that I have to decide is who sits in the first seat. Okay. So the first thing, just like here, I was looking at my first toss and I listed out all the possible things that could happen. Well, now I'm going to look at my first seat and I'm going to look at the possible choices. Well, I could pick Trevor, who I'll abbreviate T, or I could pick Ray, or I could pick Julie, or I could pick Vernon. Okay, so I'm just abbreviating their names. So that's my first seat, okay? Now, once I've chosen who's gonna sit there, now I need to make a decision for the second seat, okay? So if Trevor was in the first one, then when I go to my next seat, I'm only gonna have 3 people left, right? Trevor obviously can't sit in 2 seats. So from here, it would have to be either Ray or Julie or Vernon, who sits in seat number 2. Okay, if Ray sat in seat number 1, then from there, it's going to have to be either Trevor or Julie or Vernon, who sits in seat number 2. If Julie sits in seat number 1, then it's going to have to be Trevor or Ray or Vernon. And if Vernon's in seat number 1, then it's going to have to be either Ray or, Trevor. Forgot Trevor. Trevor or Ray or Julie. Okay. So looking at this, right, if we just had 2 seats with these 4 people, then I can see that there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 different ways. So with just 2 seats in these 4 people, there'd be 12 different ways to arrange them. But we have 4 seats. So now I have to look at my third seat. Okay, so if Trevor's in the first one and Ray's in the second one, then when I go to make my third seat, right, it's going to have to be either Julie or Vernon. Okay, if Trevor's in the first one and Julie's in the next one, then from there, it's going to have to be either Ray or Vernon. Okay, if Trevor's in the first one and Vernon's in the second one, then this is going to have to be either Ray or Julie. Okay, and I bet by now you're starting to see what the annoying thing about tree diagrams can be, right? So from here, if it's Ray and then Trevor, it's going to have to be either Julie or Vernon. If it's Ray and then Julie, it's going to have to be either Trevor or Vernon. If it's Ray and then Vernon, it's going to have to be Trevor or Julie. Oof, all right, we're getting there. If it's Julie and then Trevor, it's going to have to be Ray or Vernon. Right? If it's Julie and then Ray, it's going to have to be Trevor or Vernon. Okay, if it's Julie and then Vernon, the last one will have to be either Trevor or Ray. Okay, this guy, if it was Vernon and then Trevor, it's going to have to be Ray or Julie. If it's Vernon and then Ray, it's going to have to be Trevor or Julie. And if it's Vernon and then Julie, it's going to have to be Trevor or Ray. So 4 people, 3 seats. I'm up to, let's see, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, I think. Different ways that you could seat them. All right, and then we get our last one, our 4th seat. Okay, so when we go to look at our 4th seat here, if Trevor was in the first one, Ray's in the next one, Julie's in the next one, I only have one option from there. It's got to be Vernon, right? He's the only person not in a seat. If I've got Trevor, Ray, and Vernon seated, then the next one is going to have to be Julie. That's my only other option. Okay, if it's Trevor and then Julie and then Ray, this one has to be Vernon. Trevor, Julie, Vernon, this one has to be Ray. Right? Trevor, Vernon, Ray, then this one has to be Julie. Trevor, Vernon, Julie, this one has to be Ray. Right? And you can kind of see as we're going through here how all of these people are going to have to be chosen. I'm going to go ahead and just kind of fill this out. And you can see now, these are all the possible ways for this to happen. Oof, there they all are, right? So I could count all of these up, and that would tell me how many possible ways I could choose to arrange people into these 4 seats. So 4 people into 4 seats, there's a lot of different ways. All right. Now, as you can see here, there is a major flaw with this method of writing things, right? Tree diagrams are great because the organization makes sure that you get everything, but spatially, they're a pain in the butt. Okay. And like when we were doing this one, we lost a person each time, right? Because somebody sat down. So then we only had one fewer people left to choose from, right? Think about if we'd done something like this with like this problem, right? Where heads and tails remains an option every time, right? So imagine if like all four of these people had stayed in option each of these four times. Imagine how crazy that would be. Okay, so making a tree diagram is a good way to organize, but they're kind of a pain in the butt to make. Okay, so that's sort of the trade-off. It makes sure that you write out every possible combination, but it doesn't actually, like, it's spatially is kind of annoying. Okay. Okay, so then this last one. So we got a bag that has red, white, and green marbles. We're going to choose 2 marbles from the bag. How many possible outcomes are they? What are they? And are they equally likely? Okay, so I've got red, white, and green. So when I pull my first marble, I'm pulling 2, right? Okay, so these 2 marbles means I have 2 events. So for my first marble, right, it's either going to be red or white or green. When I go to pull the second one, and this is where you need to pay attention, because the question is it like this one where once we'd used Trevor, we only have 3 people left? Or is it like this one where after you get heads, you could get heads again? Okay, so you have to really read the question to figure out whether that's the case or not. So this one says that it contains several red, white, and green marbles. So that is implying to me that there's more than one of each color because there's several of them, right? So if I pick a red one, when I pull that out, that doesn't mean that there aren't any more red ones in the bag. So when I go to pull my second marble, I could still pull either a red or a white or a green marble. Okay, this decision, these are the kinds of decisions that people have the most difficulty with in this unit. Okay, because in this unit, these are the kinds of things that you need to think about. It's not as simple as just solving, like doing a list of steps. Like the math that you're doing is very simple, right? Calculating wise, it's deciding, do I have 3 letters that need to be written here or is it only 2? Those are the hard parts. Okay, so then when I pull a white one, I'm going to have 3 options. It's either going to have to be red or white or green. Okay, and if I pull a green one, it's going to have to be either red or white or green. So to answer these questions, how many possible outcomes are they? Well, you can count the ends of the rows to figure out how many total paths there are. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. So how many possible outcomes are there? There are 9. What are they? That's what your tree diagram displays. You could get red and red, you could get red and white, you could get red and green, you could get white and red, white and white, white and green. You get green and red, green and white, or green and green. Okay? Are they equally likely? We don't know. I can't answer that question because I don't know how many marbles there are in the bag, and I don't know if there's an even number of them all, right? It doesn't tell me. If there's the same number of red, white, and green marbles in the bag, then yeah, they're all equally likely. But if there's like 10 red ones and 3 white ones and 4 green ones, then no, they're definitely not equally likely because red's more likely to come up. So I don't have enough information in this problem to answer the question of if they are equally likely. Okay, so this is what tree diagrams are. So tree diagrams, again, so what this key difference here is, tree diagrams do more than just tell you how many, okay? They are a way to display all of the possible outcomes. If we're just looking for how many, we're going to find a faster way of doing that, okay? But if you want to actually write out what all the outcomes are, then the tree diagram is a way to write out all the outcomes and make sure that you get them all. Okay, so that is kind of what the point of a tree diagram is. Yes, I know they're kind of annoying, all right, but they are a useful tool.